Hey everyone, Professor Davis here from ChemSurvival.com, the YouTube channel ChemSurvival, and in this video I'm going to give you a brief introduction to how we structurally classify carbohydrates and a little bit on their stereochemistry as well. Let's get to it. Let's begin our conversation by thinking about carbohydrates and what defines them. A carbohydrate is a molecule with the formula CnH2ON. In other words, 1 water per 1 carbon, hence the name, carbohydrates. Now, to begin our discussion of the structure of carbohydrates, I'm going to do something you might not expect. I'm going to show you a molecule that's not a carbohydrate. Here it is. This is a molecule called glycerin or glycerol. Glycerin is a sugar alcohol, not a carbohydrate, because its formula is C3H8O3. There are too many hydrogens in this molecule for it to meet the definition of carbohydrate. A carbohydrate of this size would be C3H6O3. What this means is that to convert my glycerin or glycerol into a carbohydrate, I have to remove 2 hydrogens. So let's think about the consequences of doing that to a structure like this. To do so, I'm going to create a couple of copies, and I want you to focus on the center copy right now. Let's take those 2 hydrogens from a terminal carbon, these 2 hydrogens here. Now, when I do that to create my new carbohydrate, I create a new functional group as well as a molecule that has the formula C3H6O3, an appropriate formula for a carbohydrate. But in doing so, I also created this group. That group is an aldehyde. And so, this class of carbohydrates, where there's a carbonyl bond at the terminal carbon, these are called aldoses. Now let's take a look at that molecule on the right. To turn my sugar alcohol into a carbohydrate, I could just as well have chosen to remove these 2 hydrogens. These 2 hydrogens, when removed, create also a carbonyl group, but now it's in the middle of the molecule, a molecule with the formula C3H6O3, just as a carbohydrate should have. But this group is now a ketone, so we call this class of carbohydrates, where the carbonyl is internal, ketoses. So the 2 main classes of carbohydrates are aldoses and ketoses. But within each of those groups, there are a number of potential structural differences, so we have to classify them further. For example, here I've drawn 4 aldose molecules for you. Let's take a look at the one on the left. The one on the left would be called an aldotriose. The reason we call it this is, not only does it have the necessary aldehyde functional group, but it has 3 carbons in the chain of the sugar. The next molecule is an aldotetrose, again because it has the requisite aldehyde functional group and 4 carbons in the chain. And this trend continues naturally to aldopentose with 5 carbons, aldohexose with 6, and so on. Unlike aldoses, ketoses have a carbonyl which could be on any of the internal carbons within the carbohydrate. Although if you look closely at these common ketoses, what you notice is that that carbonyl almost always appears on the second carbon in. This is true of most biologically relevant ketoses, so that's what I've shown here. Let's take a look at that molecule on the left. Here we have a ketotriose, named so by virtue of its internal carbonyl and 3-carbon chain, ketotriose. Next, we have a ketotetrose, of course, an internal carbonyl and a 4-carbon chain. And this trend continues on just as it did previously with aldoses, giving us ketopentose with 5 and ketohexose with 6, most often seen with the carbonyl on the number 2 carbon. But the structures of carbohydrates go far beyond just aldoses and ketoses. We have to also consider the fact that carbohydrates have stereochemistry. To do that, let's consider this simple carbohydrate. And how about a little pop quiz here? What would you call this particular carbohydrate? Well, it has an aldehyde functional group and a total of 4 carbons in the chain. So we would call this an aldotetrose. In fact, this aldotetrose is known as D-erythrose. But what we haven't yet considered is that these are Fischer projections that we're looking at, which means that those carbons are actually tetrahedral, or at least carbons 2, 3, and 4. So we have to consider the possibility that we have chiral centers in our aldotetrose. And on close inspection, we do. We have 2 chiral centers. This means that having 2 non-equivalent chiral centers, there is a matrix of 4 possible stereochemistries for this aldotetrose. So let's think about each of those 4 structures. I'll start by making some copies. Now let's consider what happens if we invert both of those centers on D-erythrose. If we do this, switching the hydroxyl and hydrogens on both of the chiral carbons, we create a new compound that is a mirror image of the original, but is not superimposable. So this is an enantiomer, and it gets the name L-erythrose. As you can see here clearly, they're mirror images of one another. Let's think about the next possibility. That would be that we just invert one of the 2 chiral centers. We'll start by inverting carbon number 2, switching the hydroxyl and hydrogen to create a new compound. But this one is not a mirror image of the originals. This is a whole new carbohydrate. It's a new carbohydrate that we call D-threose. And finally, we could invert just the carbon number 3. If we invert only that chiral center, switching the hydroxyl and hydrogens, we get a new compound that's a mirror image of D-threose. So we call this L-threose. It's another enantiomer because it's a non-superimposable mirror image. And yet, erythrose and threose molecules are not mirror images of one another. So we have enantiomers, D and L for erythrose and threose, and we also have a diastereomeric relationship between erythrose and threose. So as you can see, the chiral chemistry of carbohydrates can become very complex very quickly. Not only that, but carbohydrates have tendencies to cyclize, dimerize, oligomerize, and even polymerize into huge biologically relevant molecules. We're going to cover more on the structures of those molecules in a future video. But for now, we're done considering the basic structure and chirality of carbohydrates. That's all for now, folks. I'm Professor Davis from ChemSurvival.com and the YouTube channel ChemSurvival. See you on the next video.